So the alternate title that we had for the paper was this, The Magical World of Autism. So it was a title with a semicolon. No, yeah, The Magical World of Autism.
They didn't like it.
They didn't like it. Magical World of Autism, Autism as a Disorder of Prediction. And the editor said, no, we can't have any fanciful aspects to the title. Let's just keep it dry, keep it Autism as a Disorder of Prediction. And I suppose there was some merit to what they said.
We still refer to it that way, though.
We do, right? So, and the reason why we think of this as the magical world hypothesis will kind of become clear in a moment. Okay, so this is simply to make the point that when we talk about many other conditions, whether it's ALD or ALS, or say FR syndrome or Gertzmann syndrome, if we pose a question like, what is ALS? We can say ALS, also referred to as Lou Gehrig's disease, is a progressive neurological disease that attacks the neurons responsible for controlling voluntary muscles. We can give these kinds of succinct descriptions of what this or that condition is. But when it comes to autism, what is autism? And all that we can do is to produce this list of traits that are associated with autism. We can't say what autism is other than, hey, autism is associated with so many of the traits. And you look at the diagnostic and statistical manual, and it's the same kind of picture of autism. You're presented with a bunch of traits, and you're essentially being asked, or the clinician is being asked, is the child exhibiting, 3 out of 5 or...
It's so arbitrary, and it changes every version of DFM. And it's like there's 3 areas, you have to have 3 in this one and 4 in this one, and it changes. Like it's still like it's yeah.
So it's a very unsatisfying state of affairs as far as autism is concerned.
Is it like a questionnaire that you fill, and then if you are above this number?
That's how the diagnosis goes with children. It's like a criterion-based kind of diagnosis. But a psychiatrist can sit down with a kid and just check off behaviors and say, yes, autistic.
I mean, with probabilities. With some probability. Like, what is the probability of this kid being autistic? In a very early...
No, it's like yes or no. But there's levels of support. So yes, autistic. What levels of support? 0 supports to heavy support. So like a 0 to 3. But yeah.
Like all unusual conditions, it has lots of symptoms, but they don't have to be, symptoms don't have to be the core problem of the disease.
Right, exactly.
Seems arbitrary.
And I think the diagnostic criteria is subjective, is a qualitative data. That's the key problem.
Yep.
This is how you recognize it.
That's right. Yeah, and just pointing out, it's in the eyes of the clinician.
I was curious, let's say there is a list of questionnaire which is here in America. Is this list same in India?
It ought to be the same. So people have translated these checklists for India as well. There would be some aspects to this testing that might not be culturally transferable. So people have tried to make those translations. I don't know exactly what the status of that is. But the basic procedure remains the same across countries. Yeah, so here is DSM-5. This is how you would diagnose the condition, as manifested by at least 2 of the following, as manifested by
I haven't looked into the recent work, and we published a paper on autism at some point. One of our reviewers was deeper than I was in the, let's say, clinical world of autism, and said in the current version of DSM-5 there is not only qualitative data, but also there's a quantitative aspect can be used. So let's say anything from genes, from hormone levels prenatal, or but I don't know whether, is there any merit to it? Any quantitative data other than, let's say, the repercussions?
It might be the levels of support. I don't know about anything more medical, but it's more like how much support does the person need, 0 to 3. So there's numbers that you associate to how, it used to be called severity. It's not severity. It's like how much support does this person need? And that's the only number that I think goes with it.
But it's not that, let's say we would use gaze behavior or we use, I don't know, sound patterns, because all these different
No,
No,
I
it's-
have
quantitative
any of
data.
that.
So
It's checklists like that.
okay, because I was wondering, so I was going then into the digital version of this. I can't really find it, and so
No.
luckily I could dodge that question. But I was always wondering whether that has made some progress away from quality.
No, and there's certainly no involvement of genetic information in the diagnostic procedures. Molecular biologists have produced lists of like over 100, by some estimates, over 700 risk genes, but all of them are low penetrance genes. That is, if you have that mutation, there's a small chance that you have autism. So just the existence of a particular mutation cannot be used to say that the child has autism, unlike Down syndrome, for instance. Okay, so in the DSM, there are 3 basic islands of functioning that are identified as being affected in the condition. Here are the 3 islands: social interactions, communication, and the conduct of behavior, how you plan your behavior. These 3 things seem quite different from each other. The DSM thinks of these as 3 fairly distinct islands. Okay.
He's all thinking about it. Yeah.
So this is artistic liberty. So here you have the islands of Hawaii, kind of like the islands of autism. On a map, they look like distinct islands, but if you probe a little deeper, you find that all of these islands are arising from the same basic cause. The chain of Hawaii Islands sits on a fault line. There are volcanic eruptions going on, and they lead to these islands. So what seem like distinct islands are really rooted in the same basic cause. So the question is, might the different islands of functioning challenges in autism, might they also share some commonalities? So that's the starting point for our thinking. So if you look at the literature for each one of these domains, and there is a massive amount of literature for each one of these, like how do you model social interactions? How do you model communication? How do you model how people plan their behavior? These are just a few of the papers. If you look through these papers, one very interesting thing that stands out is that the theoretical model that's often used for each one of these domains is a similar one, and that is a Markov model. So all of these domains are often modeled using a Markov system, which is a Markov system very simply is a collection of states with probabilistic transitions between those states. So you have these transition probabilities of, say, going from state A to state B. What is the transition probability B given A, etc. The crux of being able to function in each one of these domains lies in being able to estimate the Markov model that characterizes a given circumstance. So if you're in a social interaction situation, you would want to know what is the likelihood of, say, Sid speaking and then Mikhail speaking and then me having to speak. And that would facilitate my smooth interaction in this communication. So the challenge for the brain to be able to estimate this model for each one of these domains, and hence to be able to work, to function well in these domains, is the estimation of these transitional probabilities. The states are observable states, but what you need to estimate is how does one state lead to another. Yeah.
What are those errors that are going out of A, B, C, and
So
never
those
arrives
are
in-
that you are staying within the same state. So once Sid starts speaking, he just keeps speaking.
I see. Doesn't go
So,
in.
yeah, it doesn't go anywhere. So with some probability, you're just going to stay in that state. But then with some other probability, you're going to exit out of that state. So what is the key computational requirement for estimating a Markov model? It's the estimation of the conditional probabilities. And just to unpack that a tiny little bit. So if what you're observing is a transition from one state to the next, and you observe this multiple times. So see state A, and that leads after some time to state B. And you see this multiple times. A does not always lead to B, and B is not always preceded by A. So it's a probabilistic transition. But based on these observations, you ought to be able to estimate what is the probability, the conditional probability of B given A as a function of time. So after a certain amount of time, after A elapses, then B happens, and your brain has this challenge of estimating this conditional probability. So given that this is such a crucial piece of the computation that the brain has to do in order to function well in any one of these three domains of behavior planning, communication, social interactions, and these are the three domains that are most affected in autism, the hypothesis that we are proposing, the PIA hypothesis, which stands for the predictive impairment in autism hypothesis, is this: that autism is accompanied by impairments in estimating this conditional probability. Graphically, somewhat fancifully, we can view it as this. So because most of us are familiar with the contrast sensitivity function in vision, so inspired by the contrast sensitivity function, we are proposing the existence of something like an association sensitivity function, where the y-axis, instead of being contrast sensitivity, is the strength of the association between A and B, and the x-axis is the temporal separation between the two events. So how long after A happens does B happen? So in this two-dimensional space, relationship on the upper left would be the easiest to detect, because the strength of P of B given A is high. That is, B always happens after A happens. So it's a deterministic relationship. And the delta T is very short. So B happens almost immediately after A happens. So it's the best kind of relationship, the easiest kind of relationship to have to learn.
So time is interesting. Time is your Bayesian prior in a Markov model, because Markov is independent of time.
Right.
You smuggle in the Bayesian part of time, saying, okay, it accumulates and then.
That's right. That's right.
That's very interesting.
So,
well, I think in the original Markov time, there is time. It's discrete. I think they are with delta T, they're making it continuous. Like jumps are not like, in multiples of 1 second.
That's right.
It could be any.
Again, but you don't have a, let's say, in a Bayesian model, you would have prior who predicts from posterior, right? Whereas here it's always just on the fly.
Yeah.
Correct. Yes.
Yeah. So just as relationships on the upper left are the most easy to detect, relationships in the lower right are the hardest to detect. Very weak relationship, so B does not always happen after A. Rarely it happens after A. And the time that separates the two is quite long. So between these very easy to detect and very hard to detect, there's probably some kind of a threshold function above which the relationships are detectable to the normal brain or the neurotypical brain, and below which the relationships are, we are essentially blind to those relationships, even though those relationships might exist, but we simply don't have the ability to detect them. So if we accept the existence of this kind of a threshold function, what we are saying in the PIA hypothesis is that autism must or may
Then paying attention.
be associated with a shift of the association sensitivity function to the up and left. That is, the easiest relationships to detect are still detectable, but many of the relationships that the neurotypical brain can detect now become unreachable for the individual with autism. So all of the relationships in the space between the dashed curve and the solid curve.
What relationships do we refer to? Because then that leads to it's a local overload, right?
Yeah.
So
Um,
when you mean good relationships, right?
Yeah, so there are various kinds of relationships. And as you will see in two of the cases that we consider. So consider the case of me tossing a ball to you. The relationship is between the current state of the ball and where the ball is going to be a little time later. So those are the two states. Or think about an auditory sequence unfolding. So let's say a metronomic sequence is unfolding. Every beep is event A, and then the following beep is event B. So you would need to define what your event A and event B are based on the circumstance that you're studying.
One more question. What would be the impairment in the brain that would pull this curve below the neurotypical brain?
Or below, make it even better.
Even better, yeah. But it's still an anomaly, right? Would that be treated as an anomaly?
No, I think that would be a super spread.
I think you just think about like neurodivergent to neurotypical as a huge continuum, and then within each one of the continuums, you can go, keep going either direction, right? So probably IQ, right? Like that kind of thing.
Great. So that's a fascinating possibility. Whether the ability to detect predictive relationships between events is correlated with, or maybe not, with something like IQ. So when we talk about the changes in IQ or the spread of IQ, is this a correlate?
Could it be, I'm just thinking about it in the sense of maybe more pathological or maybe not pathological, but people who would make associations like superstitions, right? So those would be associations that might not be necessarily detected in the sense that they will be hyper keen to make associations between things, but they are not necessarily actually.
Yeah, that's why I said it might be an impairment. Like you're making all these hallucinative, associations, which doesn't really relate to real world.
So yes, it's a fair point. So think of each of the values in this 2D plot as a value that's been computed over many observations. So this is an ideal observer. Yeah, an ideal observer who has had access to thousands upon thousands of events in the world, and then is computing these values. For something like superstition, where there is actually no relationship between the two events, but something just happens just by chance. Say the B.F. Skinner actually wrote a paper titled "Superstition in the Pigeon," where he would just randomly drop food grains, in the Skinner box that had a pigeon, and whatever the pigeon happened to be doing at that time So if the pigeon happened to be pecking at its left feather, and suddenly these grains drop into the box, the pigeon comes to associate the existence of the grains with the pecking on the left feather. And then subsequently, it keeps pecking at the left feather with the hope that it will get that grain. So it's not that the pigeon has detected some really weak relationship in the world. The pigeon has detected a spurious relationship, which would not show up in this plot. It's just made a wrong association.
So the relationship can be impaired for A, you have just a temporal deficit. My temporal relation
Yep.
to the world is different values,
Yep.
or mine and yours are the same, but my glue to connect the dots literally is different. And again, that would go back to what I'm asking.
Yep.
This local interval, right? This weak central coherence,
Right.
temporally, basically. Is that what you're arguing?
So
So it's weak
Right.
temporal.
no, so that's a very important point. We don't know what the underlying factor for the challenge in detecting this conditional probability might be. It could be that we are not integrating multiple instances together. So to detect weak relationships, that B happens 30% of the time after A happens, you necessarily have to incorporate many observations because no single observation is going to give you is going to tell you the strength of this relationship. So for weak relationships, there is a requirement that the brain integrate multiple instances. And it's possible that the challenge in autism might even more fundamentally than a predictive impairment, be a challenge of temporal integration. So we are open to that possibility. We are saying that this is an intermediate manifestation of something that might be even more fundamental.
Obviously, it's really never thought about the temporal domain of this because we know, let's say I have two glass patterns and or I measure any of these things not temporally across time, just on a timeline. We see sometimes perceptual differences. That makes sense, but it's then across time, across all these dimensions, maybe fundamentally.
Predictabilities and integration, they're not necessarily independent, right?
They're not independent, right? So
What are those?
the predictabilities and temporal integration are not independent. I would think that they are very tightly correlated, especially when, as I was saying, when you're trying to detect weak relationships, then you have to have a strong temporal integration. Okay, so this basic idea is what we described in this paper. Dick was, there's Dick and Margaret, Tapan, Leo, who's now in California, Annie, who we all know, and Demetrius. So this was just a beautiful enterprise. I really loved writing this paper. We didn't really have to do any experimental work. We were just looking at the past data reports from other people, and we were trying to put them all into one cohesive framework. So this is the magical thing. With compromised prediction skills, an individual with autism inhabits a seemingly magical world wherein events seem to occur unexpectedly. So that's why we call this the magical world hypothesis. Okay, so let me see if I can show you some experimental results. Okay, so this is the work that Tapan was referring to, looking at sensory processing. Sensory atypicalities, especially hypersensitivity, are very commonly reported in children with autism, and they could take on the form of either visual hypersensitivities or auditory hypersensitivities, as you see here, or even tactile hypersensitivities. So children with autism sometimes are bothered so much even by little things like clothes tags that parents have to cut off the clothes tag. somewhat alarmingly, I'm also very bothered by includes tax. So the question is why? Why might these sensory atypicalities exist? One possibility is that autism actually confers hypersensitivity to people on the spectrum. That is, their visual acuity, their auditory acuity, their tactile acuity is actually better than the neurotypical.
I have to say, this has been debunked, this paper.
Precisely, exactly. So all of these papers actually have been challenged. So, but let me just for the sake of everybody's background. So this paper created quite a stir. The first one, it was called Eagle-Eyed Visual Acuity, an experimental investigation of enhanced perception in autism. And I was blown away when I saw this plot. So this is visual acuity. And you notice that there's not even an overlap between the groups. It's the autistic group
Is on the left.
And the control group is on the right.
Yeah.
Completely non-overlapping. And the autistic group has significantly higher acuity than the control group. So the number that you see on the left is the Snellen fraction. So when we talk about 20/20 vision, that would correspond to 1. 20/15 vision would correspond to say about 1.5.
Incredible.
What you notice here, what was being reported, is that individuals on the spectrum have something like 20/7 vision. Hence the name eagle-eyed visual acuity. Eagles have that kind of acuity, 20/7. And they made the claim that because of this extra sharp vision, individuals on the spectrum tend to get lost in the trees instead of the forest. So this tendency to fixate on little details may be stemming from having access to just too much detail in the image. It led to quite a bit of excitement, but then, as Jan pointed out, the paper came under a cloud because the experimental procedures that they had adopted turned out not to be good enough. And Jan, correct me if I'm getting this wrong. The maximum acuity that their procedure could have detected could not have gone up to 20/7. So even just the technicality of the numbers that they were reporting was inconsistent with the capabilities of the equipment that they were using.
It's still worth repeating because basically you need a few pixels, right? You know, dark, white, dark pixels, and then create a velocity or something. Right? So either you push your you go further away to reach that pixelation, right? Because then you can create larger stimuli.
Right.
So I think that it's still interesting, but they just didn't. And the creator of that other thing was Michael Bach.
And actually, how come they can see it's completely different two groups? At least there should be any, I mean,
some overlap. Right.
Yeah. So I think it's
still
interesting because the hypothesis of local career, let's say.
Can we rely on this?
Hypersensitivity to local features might be so.
Yeah.
Is it a true statement to say the visual acuity for just like the larger? I mean, with significance, it's some significance.
So I don't know. I haven't seen any other papers that corroborate this idea. Margaret, have you?
I haven't, but I haven't been looking either. I mean, it's interesting to like, why not try to replicate, that would
So there was a response, I haven't looked at this. There's a long review from Michael Simmons in 2009, Vision in Autism. It's just all visual perceptual tasks compared, and then there are a few other review papers on functional outputs and compared groups. Some retro analysis did this, but they all use standard tests, so they don't really go after this type of question. This type would require proper psychophysics and calibration of screen and some more thinking. I would probably need to get further away to create but even then you need pixelation to reach a certain
In ophthalmic center, is it possible to measure beyond 20 by 20 vision? I mean, the acuity, people try to measure.
Yeah, absolutely. Even on the regular Snellen chart,
Okay, they will
there
reduce
are
the
lines below the
okay.
20/20 line. Yeah.
So just to be sure I understand, are we challenging the data or their interpretation of the data? So if
We're
the
challenging the
data,
data.
so the data might, okay.
Yeah.
So
The
it's
methods
not-
was for.
Yeah.
so the method
Yeah,
is-
if you monitor max, the physics, in our test, we have a cutoff just to take care of that. So what's physically limited, if your monitor is physically limited to, let's say, 20.
So how many
or
subjects
40
they
minus one.
How many subjects they
Then you have to,
About
your
20.
psychometric functions might go beyond, but you can't.
So maybe in a
Yeah,
month
but
I can do
that-
this. I can
That's
see
right,
how it's working.
Yeah.
Okay.
And
So that's
low
the
function,
limits.
they are all low function or high function? They're low function subject or high function?
I would think that these must be high functioning individuals.
Yeah, to get them to report,
Yeah,
they would have
for
to be.
right, exactly. Yeah.
And when you say debunked, are there papers?
Yeah, so Michael Bach and the other, I think the authors of the method they used, the Fragt method, one of the inventor was Michael Bach. I think he wrote a letter, there was back and forth or some was about, because obviously this is very interesting, right? But I haven't looked into this for a long time, but I think I remember.
So nobody has tried to replicate this paper because this
Somebody must have.
People must have. Yeah. Thank you.
Yeah, Tom.
What?
Yeah, Tom.
Tom? Have a question?
No, drop. You said somebody left.
No, I just said somebody must.
Somebody must have.
Yeah.
So Margaret was saying
Oh,
somebody.
sorry,
no,
I
no,
was
sorry.
distracted, sorry.
Yeah, we should find out whether people have tried to replicate this with other high functioning individuals in most cases.
While you
Actually, I'm gonna-
look at some of the reviews. But I can't remember this but
Yeah, I believe Steve Decken also.
he did a bit, but I think they didn't look at hyperacuity or vernier or something. No. But I have a few of these papers. I know.
Thank you.
Resolved.
Then there is a similar kind of story, not as dark, but a similar story told about auditory sensitivity, that children with autism have a greater proportion of them have hyperacute hearing, especially in this case in female groups, in females. And then in more lay accounts, so here's a statement that I found quite interesting. And not unlike a dog, the child with autism may actually hear things undetectable to your ear. In extreme examples, the child has been able to hear the heartbeats of others in the room.
Wow.
Yes,
Extraordinary.
extraordinary, right? So this is how the sensory hypersensitivities have been accounted for. That the children with autism are just hyperacute. They are hearing things or feeling things that you and I are unable to feel.
But that doesn't necessarily mean their vision or their the hardware they use to process information is better. It's the brain, right, that does the processing. I think maybe differently.
So
is it the
actually,
hardware?
so I've seen some suggestions that even the hardware, the front end hardware, the packing of the cones could be higher in autism than in
It's even more extreme.
even more extraordinary, right? Yeah. Yeah.
So all the autism individual has a higher sensitivity to across all modalities, or just for vision, or
Not necessarily. Yeah. So some children might just be hypersensitive in the auditory domain, but be able to tolerate vision reasonably well.
Auditory seems to be the most
Yeah.
most prevalent clinically. Seems to be auditory, but the tactile is really huge too.
Yeah.
And vision is often the other way around, often deficits in many functions.
But just as Jan was pointing out, the first paper has come under some cloud. So Michael Bach and Steve Dacken, this is a quote from their paper. Technical limitations in the procedure used to measure acuity call into question. the conclusion that people with ASD have higher visual acuity. Similarly, reports of hyperacusis, hyperhearing, others have been unable to find these kinds of differences, and a similar kind of result of not finding basic acuity differences in touch. So that idea that the hypersensitivities could be pinned just to hyperacuity in any of these modalities, that seems not to be entirely solid. So what is another possible explanation? And here is one idea that we have considered. So why is it that instead of talking about why individuals on the spectrum have this hypersensitivity to things that a neurotypical person is insensitive to, let's ask the question the other way around. Why is a neurotypical individual insensitive to, or largely insensitive to, these kinds of stimuli? So why is the woman on the sofa not bothered by the sound of the vacuum? And the big part of the answer lies in habituation. Even though she might have been upset when the vacuum started, very quickly would not have been upset when
Not at all.
So look at the man doing the vacuuming.
Hallelujah.
Yes, I hadn't even noticed it's a gender issue, but I have been complimented very often for the choice of picture. So after that initial sensitivity, then things begin to damp down. And habituation, of course, is a very, very well-studied phenomenon. It's been observed at the level of behavior and also at the level of individual neuronal responses. So it's not controversial. But let's dig just a little deeper. What factors modulate habituation? And one of the biggest factors that modulates habituation is predictability of the stimulus. So if the stimulus is predictable, then you will habituate to it. If, on the other hand, the stimulus is not predictable, then your habituation is either going to be absent or much lower. And again, this is
For ASD.
no. This is for controls.
I see.
Yeah, in general. So if you were to be hearing a metronomic sequence, you would habituate to it.
Yeah.
But if you're hearing just a randomly timed set of beats, you won't. Right. So here's some evidence, just one of the many. So exposing mice, this is a mouse paper, exposing mice to mere temporal unpredictability within a time series of neutral sound pulses prevented rapid habituation of single neuron activity. So there is significant evidence that predictability modulates amount of habituation. And this idea actually has been used to bad ends in using music as torture. So the most effective kind of music that you could use to torture somebody is unfamiliar music, where you can't predict what's going to happen next. So if you play Bollywood music to somebody who has never heard Bollywood music, they would find it very aversive. So unfamiliar and hence unpredictable music works best. And I was also reading, I don't know if I mentioned this yet, Chinese water torture. So where you have a person with a drop of water falling on their head every so often, which seems like nothing, and everybody ought to be able to tolerate it. But after a while, it gets very aversive to have this drop of water hit your head. And what makes it even more aversive is if this drop of water comes at random times. So if it's falling at regular times, then you can tolerate it. But if it's falling at random times, it becomes very bad. In fact, Mythbusters, this television program on Discovery Channel, they did a show on Chinese water torture. And they found exactly that. that the randomness of the arrival of the water drop is what is really elusive. Okay, so reduced predictability, these findings suggest, reduces habituation. And we are saying that autism is associated with a reduced ability to predict. So the corollary, or by extension, we can ask whether habituation then is reduced in autism relative to neurotypicals. So we decided to study this with a very simple sequence of metronomic beeps. And this is the work that Tapan was talking about, just getting galvanic skin response, very simple assay, while people are listening to these beeps that are arriving once every second. We followed this up with MEG and also with EEG, because we were getting such beautiful results with GSR. I could not believe that this could be a real finding. So we wanted to be very, very sure. So here are the results. So this is the GSR trace, galvanic skin response trace, or skin conductance for one neurotypical subject. And you notice, the time is in seconds. This is about 6 or 7 minutes. And you notice that, unsurprisingly, the response is decreasing, the person is habituating. Here are 2 more individual subjects, again, habituation. And here is the average trace across 18 participants. Beautiful habituation.
Are the little jumps when the
The little jumps can be like movement related.
No, this is due to, the jump, what you see here. Initially, it was in rest.
Oh, right.
And we started presenting the beep, all of a sudden it jumped. And then it come down, then slowly.
Right, you're right. Yeah. So there's a period of silence.
So the scaling, both the cases are not same. This is the individual graph, but it's the average one, but the scale is different. That's why you can see around 100, you can see the jump, but here you can see around 0. So we have just shift left side when we presented the string line.
Yeah, so it starts with the silent phase and then the beat suddenly start. And that start of the beat sequence leads to a sudden jump, and then you again habituate. Okay, so the overall story here is the expected one that people
It's perfectly periodic, right?
Perfectly periodic, once every second. But now look at the ASD traces. So, it's really quite remarkable. This is just a recording glitch, so ignore that. But it's really quite remarkable. So 3 individuals, and here is the average of 18 participants. And here are individuals, so all 18 laid out end to end, and what you're seeing are the slopes of these plots. So positive slopes would correspond to the upward rising curves, and negative slopes would correspond to the habituating curves. And you notice
increasing, not just
why not just flat? So actually you do see mostly flat. So you notice that for most of the ASD participants, the slopes are near 0. Some of them are showing positive slopes, but they are small positive slopes. So these 3 are, I would say, not entirely representative of everybody else. The rest would be more flat.
Average also.
Average is also kind of flat. But it's the difference between ASD and NTs is still quite stark, that the NTs are showing these mostly negative slopes, and the ASDs are showing either 0 or even a little bit of positivity to the slope. So that was GSR, and you can imagine why I was a little concerned about the data being just a little too systematic, given how messy AST data typically are. For us to be getting such consistency made us wonder. So we decided to look at
Just one question, the GSR data,
Mhm.
I'm not nodding, so you put something on the hand palm,
On
and then
the-
and you measure electric conductivity.
Mhm. Yeah.
So impedance basically, or what is it exactly what you measure?
So it's the conductance of the skin, which is a function of how much wetness, how much saline has been produced by the sweat glands.
Could there, I mean, just plain devil's
Mhm.
advocate, could there be just based, it's any other condition which led to this flattening or let's say even positive slope, which it's nothing to, because the implication here right now, it seems to me that there's difference in behavioral response to reflect electric changes.
No,
Has it to do with let's say some secretion or some physiological change?
you're absolutely right. In fact, so that's why it was important for us to go straight to the brain. So to look at the peripheral.
So even let me add one point.
Mhm.
Once we did one experiment. You and me both recorded the GSR signal with respect to some interesting video, and which is not interesting to me, maybe very interesting to you. And when we both are watching Sakira's video, that World Cup Sakira's song
Waka Waka.
Waka Waka, and both of us, our GSR, are following each other.
I thought that secret was secure.
Yeah, so we tested once that whether the GSR is a strong indicator of your behavior or not. And we found it's strong indicator.
So remind me to come back to that, because I think in that observation, we have potentially a very powerful way of predicting which song or which video is going to do well in the market.
Oh, that mean 100 million.
This is essentially like, lie detectors.
Yes. Yep. All right. So we moved on to MEG, where again we were presenting these metronomic beeps, and the idea was record the evoked responses and then see whether the evoked response to the first beep versus the last beep shows evidence for habituation or lack thereof. But of course, MEG signals, like all electrophysiology signals, are quite noisy, and one can't just look at individual responses, but rather you have to average several presentations to get the evoked response for the first section of the presentation and the evoked response for the later section of the presentation. And then you can compare these averaged evoked responses and see whether the response has actually decreased, which would be consistent with habituation.
And there's a delay too?
No. Well, they could have been, but we were looking primarily at the amplitude reduction. We did not look at the
that might be interesting.
Could be because the temporal hypothesis could be tested.
It could be indeed. Yeah. I think that could be very interesting. So here are some results. Let's look at neurotypical data. In green is the average response to the first 50 beeps of this, I think, 300 beep sequence. Yeah, 300 beeps. So from this 300 beep sequence, we take the first 50, average the brain's response to those first 50, and we get the green average evoked response. And then we take the last 50, and we look at those. And as we would expect, consistent with habituation, there is a reduction in the amplitude of response. So here's subject 1, here's subject 2. So in both of these subjects, we are seeing the reduction. Now let's look at autistic participants. See the increase in amplitude in going from the first 50 to the last 50. So here are 2 ASD subjects, but we can now look at the data.
And the latency is shifting.
Yeah.
And the latency.
That's
right.
interesting.
Yeah. Here are the data across I think 12 of the participants. I think we finally had more than these participants, but even across just 12, it's quite remarkable. Again, the consistency that we're seeing. So what you're seeing here in black is the amplitude of the first 50 trials, the evoked response of the first 50 trials. In green is the amplitude of the last 50 trials. And you notice this beautiful consistency across all of the NTs that there is a reduction in the response amplitude. And you see exactly the converse in all of the ASD participants. The amplitude for the last 50 is
So we
higher.
presented 300 beeps.
Yeah.
Mhm.
So it's a 50 and the last 50.
So it's again saying shivers of fear down my spine. How can the data be this consistent? So we then also did.
Do you
Yeah.
mind, can you just follow
Yeah,
my
yeah,
background? I'm
yeah.
not sure. So basically here I see more or less, if I draw another line between the points like this, goes linear down, whereas here I see a slope.
It's individual subjects.
These are individual
Ah,
subjects. Yeah, yeah.
And the scale is much smaller. The
Yeah, scale is
overall
different.
This
response
opposite.
is smaller. Yeah, but the overall, yeah.
Yeah, these are Z scores.
Mhm.
Yeah.
Just a curious question.
Mm-hmm.
Can we say like after certain number of beeps, person is habituated because you consider the 15 trials first?
Right. So
last-
we
Very
get to that in the EEG experiment. Okay. So next we move on to EEG. Again, the same basic idea.
How many participants?
So here I think I'm forgetting how many. This is published. Let me see. So 21 ASDs and 10
Oh, I see.
NT.
Yeah.
Sorry, 10
Okay,
ASDs,
I see.
21
Yeah.
NTs. Yeah. So this is work that Wasifa led. Have you heard from Wasifa lately?
Yeah, yeah.
Yeah.
Yeah, I was supposed to see her last summer, but I haven't seen her.
No, you've seen her. You forgot. She came during my time.
When did we see Wasifa?
She came, I mean, when I was about to leave. Wasifa.
Yeah, yeah.
Oh, yeah.
But recently.
I haven't, she's on like Seattle or something.
Yeah, she moved.
Yeah.
Right.
So I haven't seen her since she moved. I was supposed to see her right before she was moving,
Right.
but we didn't get together.
So
Was experiments are running in
Well, I
India
saw her
or
during
in-
COVID. I did see her here during COVID. So whenever that was, whenever COVID was.
her daughter.
Started her own lab.
No, so she moved to. She joined a company. I think she was with Amazon or Google.
I'm not sure. I was a startup doing EEG in
Oh, she's
education.
the one who introduced Matt.
Matt.
to it.
Right.
See your daughter?
She has a daughter, Noor.
Very cute.
Yeah, yeah. Well, okay, so the EEG protocol is essentially the same as the MEG one. And here is an individual subject. So Chetan, to your point, what you're seeing here is so this is the average. I think.
She did like a sliding window of
Yeah,
ERP.
yeah. Right. She did a sliding window, but the nomenclature seems to suggest that these are individual trials, that she is getting the
Mhm.
amplitude for each
Or it might be
trial.
accumulated up to this, up to this, up to that.
Yeah.
Individuals.
It looks like some sort of pattern.
So these are,
Yeah.
yeah, one subject, one subject.
One subject, yeah, these are two individual
Right?
subjects.
It looks like all patterns look similar at the sinusoid.
Mm-hmm.
Maybe,
yeah.
Yeah,
Mhm.
we'll have
But how
to
do you calculate amplitude? Is it the maximum? Is it the average for a specific time frame?
maximum for a particular time frame. So
Timeframe.
she calculated what was the point on the average ERP or the ER evoked response potential. Yeah,
Yeah.
ERP. And at that time for individual trials,
Yeah.
she could try to see what was the maximum for any individual trial.
Maximum.
Yeah.
I see.
I'm not entirely certain whether there's any kind of sliding window happening in these plots, but we can look more closely at the paper. But let me convey the gist of the finding to you. So here, again, we are plotting the slope of this temporal progression of the amplitudes. And you notice that for many, though not all, of the NTs, the slopes are negative. And for many, though not all, of the AST participants, the slopes are positive. So it's largely consistent with the GSR and the MEG results.
And are these the same participants that did the other studies?
No,
or different
no, these
studies?
are different. These are different.
Because I guess you said not everybody exhibits auditory over.
Yes,
So
just
it
like-
could be that some of the ASD participants are not like
Yeah, I don't think that's
So even the
necessary.
previous-
matter.
I don't think it's
Even the
related.
previous result, what you have seen here, participants from India, as well the participants are from US. They're
In
from,
this one.
no, the previous one, the GSR,
The GSR
Oh, the
study,
GSR.
we did it twice. So the 18 participants each were from the US. But we had a separate study that Tapan had done in India that we didn't even report in the main body of the paper. We put it in, I think, the supplementary section. So that finding is quite secure because the Indian results showed the lack of habituation. The American results showed that MEG results showed them and EEG not.
But I think that her point is that the kids who have auditory sensitivity. Yeah, okay.
Yeah. So hold on to that point because I think Wasifa did a correlation between the index of habituation as derived from these electrophysiological measures and the scores reported on the clinical scales. Okay.
I can see you.
Do you show it?
Thank you. Let's email. Yeah.
I should. But before we get to that, Wasifa also looked at whether the reduced habituation in autism is specific to audition or does it also apply to other sensory modalities? So she created a sequence not of beeps, but of flashes, like this. So this is now a visual metronomic sequence where you are seeing this circular checkerboard appear once every second. And the story turned out to be the same, that even with the visual sequence, you would see mostly negative slopes for neurotypicals and mostly positive slopes for ASDs. And then she made a composite habituation score. So you can derive a habituation score, I think, based on the slope of the curve. You can put together the scores derived from the auditory experiment and the scores derived from the visual experiment, because these subjects had participated in both auditory and visual experiments, and see what is the composite habituation score. And this is the result there. So this makes it quite convincing that there is a difference in the habituation profile of the two, as you can also tell from the p-value. But now here comes the point that's relevant to your question, Mikhail. Wasifa calculated correlations to test coefficients between the composite sensory response profile, so this habituation derived score, and clinical scores such as SCQ, sensory
That's social communication
questionnaire,
Yeah. Child behavior
checklist, and sensory profile, something
short sensory profile.
short sensory profile. And here are the correlations. So the habituation scores do seem to correlate quite nicely with higher order things like social proficiency, and also things like the sensory profile scores. You see here, the short sensory profile.
I think that child behavior checklist is so interesting. Yeah, it's like a measure of psychological well-being or psychological dysfunction, and the habituation is so strongly correlated with that, which is so compelling. So this is competence versus syndrome. So competence being healthy, psychologically healthy, and then syndrome being psychologically unwell. So I thought that was really interesting.
We use also autism or the empathy quotient questionnaire.
We have the SCQ, which is the social communication questionnaire, sort of like a stand-in for autism, but the ADOS itself was only with the autistic kids, so we couldn't really look
Okay,
at.
but that's the one we should finish next, right?
Yeah.
So we used in our studies the AQ and the
Yeah.
EQ, just because they're simple to do.
These are younger. The AQ is like self-report adults.
Yeah.
And the kids can't do that.
Yeah, no, that's fine. That's fine.
Yeah, I know that we are running over time, but you get the basic idea that the GSR, MEG, EEG data suggests reduced habituation in ASD. And at this point, we felt, okay, now we should publish.
Now we can-
So I'll skip through this. I don't think I mentioned. So these slides actually predate when we published the papers. So there are two papers, one with Tapan in the lead, describing the GSR and MEG data, and the other one is Wasifa work on EEG. And I'm going to close with just a couple of videos because I really love those videos. So as I was saying to Jan, the linkage between states, or what one considers states, in the habituation experiment, it was beat 1 is state A and beat 2 is state B. When you're talking about interacting with the dynamic world, the state of the world right now is state A, and the state of the world a little later is state B, and you are trying to learn this association between how the current state predicts the next state. So that idea exemplified in the context of, say, catching a projectile. So if I throw a ball to you and you go ahead and catch it, that indicates a predictive ability, because it's not just reactive. You are predicting where the ball is going to be at what time.
Is it first something that children diagnosed with autism are less proficient in?
Yeah, so let me.
Oh, is that very
Well, you will be very surprised. The paper we published is in a dynamic binaural rivalry task. You have four different principal states, and you use the Markov model to show control group has a very different Markov likelihood.
Wow.
Everything you just said, we have it, and that was a key part of our paper. We didn't cite you, I didn't know about it, but we exactly show that.
Wow.
We show that we implement, as you do, as some Bayesian prior, so to speak, in this Markov model, and we show that controls and autism show different behaviors in a dynamic perceptual changing task across time. It's exactly what we show.
I would love to read that paper.
Yeah, it's very, I didn't know what, so now I'm thinking this is exactly what we show.
What was when you did that work? What was your hypothesis that you were trying to talk about?
Yeah, so I came from a obviously vision and binaural rivalry angle to that, and I knew, and at the time I read a lot about vision and autism, and I noticed that rivalry is a potential great marker for showing differences, measuring this may relate to imbalances between excitation and vision. So there are lots of theories about what is autism and what we also discuss some of that. And rivalry is a good marker to behaviorally test whether you, let's say, suppress a stimulus or you see something, so there's some excitation. Right? So firing versus suppression, so GABA and glutamate, basically. And people have done a lot of research on this, and there was a lot of evidence to suggest, okay, this is probably something useful, and we used a different paradigm. We used classic rivalry, where we have different types of stimuli in one eye, and then we use a more complex stimuli grouping, which requires both eyes to combine portions of each image and simultaneously suppress portions of other images to interocularly bring, let's say I have in one eye a little bit of this and a little bit of this, and then the other eye, the other way around. Some neurotypical people still able to see vertical or horizontal, and people with autism have that ability, but it's reduced. So that's one of the things we show in this. And then we use Markov to figure out what's the relation between these different things. So that I came from that angle to autism and more from a sort of binocular vision background. But then I realized, okay, if I'm digging into this, these principles which I learned in Rivalry actually are very useful for imbalances in the brain, in particular in autism. So very different angle, but very interesting.
Yeah, amazing to hear of the convergence. So here's a quote from a person on the spectrum. He says, throwing a ball was not a problem. However, I couldn't catch a ball until I was 13. And this seems to be a common refrain that simple things like playing a game of catch turns out to be remarkably difficult for many people on the spectrum. This is one of my favorite videos. So this is a young Darius with one of his friends, Chechi. They've known each other since age 3. So here
Is he like 6 or 7?
He must be 6 or 7. So notice how Chechi is behaving in a predictive manner, wringing her hand.
You're very excited to play this game too.
Right. As soon as I said, I'm going to use this video in my talks. Oh, so excited. This is Darius and Chechi. And then another video that I also love.
Oh,
This is a young Walter, Margaret's son.
my son.
Notice the red hair. So Margaret is playing catch with him.
That was a good one.
That's a good one. Yeah.
That's more difficult.
Who's this person on the?
It's the line, the drawing.
Somebody drew it. Yeah.
Hmm. The brain. Like that.
That's classic. Classic. Walter. Yeah.
However, we know that stereo vision is also impaired on average, and people with autism.
Sorry, what is?
Stereo vision, binocular vision is impaired in people with autism.
Oh, I didn't know that.
And obviously that then also is a
Confound.
so well. So then there's a question: hey, is the I mean I don't know this obviously, but you can't catch a ball if you haven't had stereo vision. That might be the underlying reason rather than
How is it
Then you are
diagnosed?
typical.
How is it diagnosed that stereo vision is
with
impaired?
so that the fin tests are typically use glasses which separate 2 images from each other with a little horizontal offset. And then if you do this, then you see 3-dimensional images, something pops out. So typically the titmus test where you see a fly popping out, or when you're in the cinema, 3D cinema, these types of glasses, where green or other glasses, they use this principle and then measure different, let's say, the stereo acuity. So there are a lot of clinical tests.
They're not based on their behavior.
No.
No, this is often when children can't catch the ball. So when that's we notice, when there's often what is it? And it might be just the eyes that you just have more stereo. Because I remember something on Twitter when Simon Baron-Cohen and people in that space who worked at posted some of this, and I was saying, hey, could be also because there's evidence on that.
Did you were saying something?
Yeah, I think that what is well illustrated there is the repetitive behavior. There is no learning. There is repetitious activity, which is a motor characteristic of autism.
Yeah.
There's no movement from one state to another. Frequently, if you use your diagram, it just circulates around the original thing. Instead of progressing from A to B, it goes from A to A.
Yeah, it's almost as if it's an attempt to introduce some predictability on the world. So instead of dealing with an unpredictable external environment by having repetitive internally generated.
Definition of predictability is that you do something.
Right.
Yeah, and it shows cognitively as well,
Mm.
because we even put it in the paper that you have a musician who can write music. Usually, it's a matter of what can I say? It is music, but it is by rule. By rule,
Yeah.
nothing new.
Straight.
For example, if there's a voice that has one pitch, you're not going to see anybody, the composer put in a diminished fifth for
Yeah. So,
that. It'll be something in the key.
Not creative.
And, well, yeah, but that takes more probability to creation.
so Margaret was describing something very interesting.
Predictability. I mean,
Yeah, I have a
Yeah.
friend who's a jazz musician, but plays very like, well, I don't know what you call it. Yeah, freeform, spontaneous jazz, right?
Mm.
And he was performing locally with a group just to sort of perform because he was in town. And I went to see it, and then I met and then he was talking about the players, and they said they were all straight. They were all straight musicians, and I'm like, they're all autistic. Do you know that? It was like, so he didn't like playing with them because they were all imitating what they had heard before. So even the improvisation is not improvisational. It's like here they heard Coltrane do this thing, so I'm going to do it. And he is much more like he just makes it up as he goes, kind of thing. So it was just really interesting to hear somebody describe this. And then I met the musicians. I was like, well, I can tell you why they're
Did you
all
learn to play jacks?
Walter.
Yeah.
No, that will be the fine motor there between. But he's a really good basketball player. That kid. He loves basketball. He loves all the balls now.
Now he's taller than me.
He's huge.
It's
interesting.
It makes sense when I think about it now. When you have internal circles more than others, then basically you have an avian an effect, right? So reinforcement learning. And in some way we can't even compare them, right? So the question would be in an experiment, right? If you take this away, if you really train two groups on a novel task simultaneously, so you break that, then you don't have this bias, because some of the data we are looking at, let's say, okay, if your internal bias is just more reinforcement rather than breaking that loop, then it's not surprise, right?
Yeah.
So that's interesting.
Just show you a couple of very short videos. So this is a game that we programmed up.
I'm gonna say, is that your experiment?
Yes, Pong. So this, of course,
nice.
comes from the original Atari Pong. All of you are too young to remember Pong. But Pong is this ball bouncing around and you playing with the paddle. We created a one-room version of Pong, where the goal for the player is to keep the ball within the room with this paddle. The ball can bounce around on these three walls, and then when it tries to escape the room, you have to block it with the paddle and put it back to the room. So here is a neurotypical participant playing Pong. And what's interesting to see is their eye movements anticipate where the ball is going to be before it gets there. And next we will see a sequence from a person on the spectrum. So now notice that it's following the ball rather than anticipating where it's going to be. Gadi, were you trying to say something?
No, I was coughing.
And then we analyze the data. And the finer grained analysis beyond just eyeballing the data. It bears out this observation that most of the fixations for NTs are leading fixations, and most of the fixations for the ASTs are lagging fixations. So here, a very young terrorist. So in Jagmar's lab, we ran quite a few studies of dynamic interception. Yes, hard to believe. And there's a lot here, but let me just try to see if there's any other slide that I want to show you.
Walter's ponytail, that's the cute one.
Yeah, right. Data, but let me try to wrap up. Yeah.
Sorry if it's
No.
very and I didn't get calculated. Sorry. But so what's kind of the next thing to look for? So if autism is a problem of prediction, what
where do we go from here?
Yeah, where do we look? Is prediction
so
is a kind of
I think this connects to the question that Jan brought up. What is, so even let's say we accept that there's some challenge to the prediction system of the brain. Is that the very bottom of this hierarchy? Or is there something even more fundamental that explains why there is this predictive impairment? And something even more fundamental than prediction could be the ability to integrate instances across time. So we don't know whether that's the case, but I think that would be an important avenue for research. Because once we get to the root of what is it that's causing a predictive challenge, which then can cause all of these other manifestations in terms of traits, then we can target that root cause. So if it's an integration across time, we could potentially think about what might be interventions that can increase the temporal integration windows. We may not succeed, but at least we have a target for what to go after.
And one more question. I guess you mentioned that your son is playing basketball now. So is that something that people learn to somehow overcome? Because I guess we must be able to catch him.
Yeah, I think the dosage of the exposure just has to be a lot more. I think that
the integration has to be more.
Yeah, I think many more trials. Like even within the context of the lab, when he was like the pilot subject, he would be all day, well, for many hours anyway, catching balls and not doing well. But then, years later, I feel like he's making progress now that I would never have thought he would be making at the age of 18. So even his language is coming along better. Like it's just all the therapies are aimed at these kids who are 3, 4, 5 years old, and then they stop. And I feel like we're missing out on a lot of like potential benefit with older people. But yeah, I think it's just like way more exposure than a neurotypical person. So,
this is a question is when I think about the Pawan experiment. If you would train that at this person,
right.
Can you bring it can you train it to the same, let's say, ocular gaze behavior? And if so, are you even comparable or are you not? So is it actually an eye movement problem here, or is it actually something deeper, right?
Yeah, I think that's a fascinating question. And does improvement on the Pong task translate into improvements on other tasks that rely upon prediction? Yeah. That I think would be amazing if that were to be the case, that you teach a child how to be better at catching a ball and you somehow get this improvement on other skills that are unrelated to ball catching.
Not only this, I mean, just seeing in the one domain, whether it is able to translate to the other domains or not.
Yeah, exactly.
I'm playing devil's advocate because this is right now a huge thing, I think, in the autism community. Obviously, I say when we consider this as the spectrum, right, as Sam Berg-Cohen often concept. Do we actually want it to be? Right?
Do we?
Right? Is it actually? I know on a very severe end of things, that's one condition, but it's really a question because essentially I see it almost like a personality trait on which we all sit somewhere, right?
Yeah, I think Margaret is
Yeah, I
best,
I think
able to
treating
answer
it to change people essentially as not autistic or to make them act as if they're not autistic is one thing. But supporting people and helping them get more language, I think that stuff is totally reasonable to do.
Yeah.
Because if you don't have language, life is really hard. If you can't navigate a parking lot, life is really hard. So supporting people, but not fundamentally changing who they are is, I think, where we need to go with intervention generally. But yeah, as far as, who cares if people have good eye contact? I mean, there's so many things that are done in therapy that are completely meaningless.
I remember when I published this, many people who, many people with autism and wrote me.
Yes.
And they're very interested. And again, all the participants were very interested in this, and they want to learn about, themselves, and they're really helpful. And during this time, I didn't know much about autism, but then I learned about neurodiversity movement, and then there are different views within the community of, we want treatment, and no, we are fine.
Yeah.
Right? And of course, there's then severity aspect, because we had a few participants which were very severely autism. And this was clearly they also communicated that to me. This was something we really struggled with, whereas others, if I wouldn't have known through the you didn't notice anything very outstanding in their behavior and in their being, so to speak. So that made me a bit sensitive to
You have to be.
to that environment when we talk about the treatment.
Yeah.
But I mean, catching a ball, if it's really for stereo vision, that's generally not something you always want to treat, right? Whether autism or not. That's something you suffer on.
Yeah.